Let's continue our discussion of BGP peering and just doing a bit of a deep dive into how BGP peering works and some of the things dealing with that particular thing. Let's begin here. Link local next hop with IPv6. Well, honestly, link local next hop with IPv6 is a total and complete disaster. There is an RFC 2545 which is supposed to define how v6 works in multi-protocol BGP, and you'll find this statement: an IPv6 router must have a link local next hop for which all directly connected routes for which the router and the next hop router share a common subnet prefix. Link local addresses, however, are not well suited to be used as next hop attributes in BGP4, given the rules defined for this attribute in the protocol specification. For the above reasons, when BGP4 is used to convey IPv6 reachability information, it is sometimes necessary to announce a next hop attribute that consists of a global address and a link local address. In other words, because BGP speakers must have a v6 link local address, sometimes it's going to make sense to advertise the BGP route with a link local next hop. However, you cannot use a link local next hop beyond the immediate BGP speaker. You can't use it from off segment. So you have to find some way of having both a global and a link local address in there. So let's say, for instance, that we are peering between C and B, and we are using the link local next hop here, and then here again between A and B and A and D, and we are using the link local next hops here. The problem is obviously going to be if A sends a route to B, and now B does not change the next hop for some reason, specifically if it is an iBGP peering session or a route reflector or an eBGP without changing the next hop. It's learning from eBGP, say this peering is eBGP and this peering is iBGP, then the next hop will not be changed by B. Well, if that is true, then what C receives is a route with A's link local next hop. This is not a good thing. In another sense, if C is again advertising something towards A and B is not changing the next hop, it could be that A has a link local next hop for C that is identical to the link local next hop for D. So this is not a good thing. This is where you run into problems with link local addressing or link local next hops in BGP. Now, according to RFC 2545, a section of which we just looked at, the way you resolve this is that in your next hop field in v6, it is normally 16 octets. And this is to cover the entire space of the IPv6 address. What you do instead of having a 16 octet address is you increase the size of the field, the length of the field, to 32 octets. And this allows you to stick two different next hops in the next hop attribute within BGP and the BGP advertisement. If there is a single address, if the length of this next hop field is 16, there is only a single address, and that single address must be the global address, a globally routed address, a routable address in v6. If, however, this field is 32 bits, according again to 2545, the length of the next hop field must be 32 octets, and the first address must be the global, routable, and the second address must be my link local. So the BGP speaker receiving such an advertisement simply looks at the next hop link field and goes, oh, well, I have a 32 octet next hop field. So what I'm going to do is I'm going to assume the first 16 octets are my globally routed address and my second 16 octets are my link local address. But what if I have situations where I simply don't have a global address for my next hop? This could be true on point-to-point links, for instance, in a data center fabric where I am carrying point-to-point peering on the interface addresses, and I never really have a multi-hop situation where my link local next hop would be ambiguous. In this case, I only want to carry a single link local address. Well, how can I do this? According to 2545, I have to have a globally routed address in the first part of that 32 octet field and a link local address in the second part. Well, Implementations do different things, and this is where things get really sticky. Some implementations will put 0:0 in the global and then the real link local address in the link local portion. Some will put the link local in both the link local and the globally routed address. Some will do a 16 octet next hop field and put just a link local address in. Some will do a 32 octet field and put the link local address in the globally routed space and a 0:0 in the link local, and just use that as a signal to go back and use the link local address as the correct thing. There is no standard way to do this, so most implementations just accept almost any combination or pairing, and they just try to figure out what's going on internally. There are some of these that will crash certain routers or cause failure modes of different kinds, so you have to be careful about link local addresses in BGP v4. There was a draft put out to try to solve all of this, but it turns out that the community wasn't really interested in solving it because everyone's implemented stuff differently enough that if anyone moved along and fixed it in the way the draft that was put out says, it would break someone else's implementation. So you really don't have a lot of choice right now. Things are just what they are. Now, when we get to dealing with the BGP Open Message, one thing you will discover is that the AS number, the local AS number, is contained in that open message. And that means that if you see an open message from a BGP speaker that you're connected to physically over some sort of a network, what's going to happen is you're going to look at your local configuration and determine if you've been told about that peer. And you're going to make sure that the origin AS or the peer's AS in their open message matches your local configuration. Well, this is really cool, but the problem is that what if I want to have a situation where I have hundreds or thousands even perhaps of peers, well, maybe 200 or 300 peers at least. There are situations, for instance, as route servers in IX fabrics, IXP fabrics, where this becomes a problem. There are situations at edge providers where they have 200 or 300 customers connected to a single virtual or physical device that is peering with all of them. This can be a problem in DC fabrics where you have a fan out of, say, 16 or 32 peers per BGP speaker. So this can be a major problem in terms of configuring things. So how do you solve this problem? Well, most BGP implementations have the idea of doing promiscuous peering, or accept all peers. Now, the idea here is going back to the way BGP builds peering sessions is one of the speakers is active and one of the speakers is passive. The active speaker always sends the open, and in the open message, it reveals what its local autonomous system number is. So what you can do in BGP is you can force one of your peers to always be the passive peer, and then tell that peer to simply accept any peering session with any peer that comes up. If it receives an open, accept it. I don't care what my local configuration happens to be. I can garner or gain or understand or learn what the remote AS is for that remote peer is from looking at the open message. So what I do is I sit here at A, I move myself into passive state, and then if B sends an open message, what I do is I look at the AS number in the open message and I say, B's AS number must be 65,000, 65,001, whatever it happens to be. And I can dynamically build the correct data structures internally at A to accept that peering relationship. B doesn't even know this is going on. It just knows that A is always passive, that it never forms an adjacency with A until B itself sends the open. So by setting A as passive, I can actually set up this situation where I can accept peering from any BGP speaker in any other autonomous system. And this again is called promiscuous peering or accept all peers. There are various names for this. This is really useful in many situations. It's something to keep in the back of your mind when you have a lot of BGP peers and you have the ability to set one of them as passive. There is an important point when you deal with this, however, is that this passive peer is an attack surface. So if you have set yourself up to accept peering from anyone, anyone can peer with you. So some Providers who do this will set up MD5 authentication or IPsec on top of TCP or TLS on top of TCP, something like that, to make sure that the peers that they're receiving hellos or opens from are actually peers that they want to receive opens from. So this is something to consider. This is an attack surface. This is opening your network to attack in a very important way if you do passive peering. Now, let's look at something called BGP capabilities. In the base BGP4 specification, which is RFC 4271, if a BGP speaker receives an open message with one or more unrecognized optional parameters, the speaker must terminate the BGP peering session. What this means is this means that if two BGP speakers come up and start to try to peer, and they don't have the same sorts of capabilities, for instance, they don't manage or support the same address families, then they simply cannot peer. This was deemed to be kind of wrong or a bad way of doing things because it doesn't allow BGP speakers to be upgraded over time. You know, there's an old saying, Pastel's law, be generous in what you accept and very cautious in what you send. So what you're trying to do here is you're trying to figure out how to use the BGP open messages or the way that BGP peers in order to allow BGP to be upgraded over time. So what happens instead is that there is an optional capability that's been added by RFC 5492 that allows these peers to say, I'm going to support this. The receiving peer, the peer that receives that open message with that particular set of capabilities, as they're called, will then say, I don't support this or I don't support that. And they'll send back a notification saying, these things I cannot support. When the sender of those capabilities receives that notification, it now has the choice of saying, I will either continue the peering or I will simply send a cease notification with a cease subcode of, I don't want to peer with you because of an unsupported capability. And you can see that right here in the text from 5492. So this allows you to have BGP speakers that can be upgraded over time, and you can have it where certain capabilities can be rolled out through a network over time, or you can have multiple address families that are supported by one peer and not by another. Now, the best place to get a full list of all the capabilities is through the IANA. So the Internet Numbering Authority actually keeps a list of every capability that is possible within the BGP ecosystem or within the BGP Open Message. And you'll notice that each one of these capabilities points to the RFC that defined that capability, or the draft, as the case might be. This allows you as an operator or as a user of BGP to go back and figure out where that capability come from and understand what that capability code actually means. Now there are some here, octal 63. You'll notice here that these are decimal, by the way. 0 through 9 is decimal. And then we go up to octal 63, and everything higher than 63 is specified in octal rather than in decimal. And actually down here, it really doesn't even matter because octal and decimal overlap at this point. But at any rate, you'll see that there are some, like 63, that are unassigned, 74 through 127. Another interesting thing is that you will find some of these are routing policy distribution or long-lived graceful restart, some things you may have never heard of, and that may be because they were never, ever really implemented by anyone. Now let's talk about one other interesting thing about BGP peering, which not really recent, but within a couple of years, and maybe perhaps some people don't know about. If you have a situation where AS 65001 and 65002 are peering, and let's say the 65001 is a non-transit customer of 65002 and 65000. So anything that is sent from 65000 towards 65001 should terminate someplace within 65001. It should not be routed through B back up to 65002. Now let's assume for a second, however, that the operator at 65001 has just purchased both of these links or has replaced this router or done some upgrades on B. What's going to happen is when they configure B, if they don't configure any filters, any routes advertised by A to B will be automatically re-advertised using eBGP up to C. 65001 is now a transit between 65,000 and 65,002. We don't want this. We want this to stop. This is where we get into unintentional route hijacks in BGP and all sorts of security incidents. So in RFC 8212, this is a BCP, which means it's a best common practice. It instructed implementers of BGP to design their BGP implementations such that if B comes up and peers with A and C via eBGP, and there are no filters of any kind at B, it should be treated as a block all routes, or you can say a deny all routes. So no filter means deny all, and that's what that should mean. So in order to get B to advertise anything, you need to set up a filter that permits something or denies something, as the case might happen to be. So this again is 8212 and RFC 8212, and every BGP implementation should be following this specification. Now, this is kind of painful in a data center fabric because you don't want to have to set up null filters just to allow everything on every peer. So what happens here is some implementations, such as FR routing, will have a knob that can either be compiled or turned on globally on each BGP speaker to turn 8212 off. Now, of course, this is dangerous if you're using a BGP speaker as an edge between real upstream providers and stuff. But this is just to let you know that kind of thing is out there, and to think about it when you're peering, that if you see no routes and you're not advertising anything, or you think you should be and you're not, then what you might need to do in this case is you might want to set up a filter because of 8212 is taking effect. All right, so that's it for peering specifically. Next time I'll come back and I'll talk a little bit about BGP message formats.